Hello, and this is a talk about weather and climate attribution, aims to outline the method that we're going to teach you to use in this workshop. And I'm the lead on this, but I've been assisted by Boon Dong, who is at the University of Reading National Centre for Atmospheric Sciences. The outline of this talk is, first of all, I'm going to give you introductory material, and that sort of is a short part. And I would say that the talk is divided up into several parts, so they'll be available as short videos. Then trying to think about what the causes are, natural or anthropogenic, in terms of event attribution, and then approach using atmospheric models, which is the core approach we get you to use, but also using couple models, which we found in the past that some groups find quite useful, particularly as a way of improving the robustness of their study. And then finally a short section on communication and ethics. So this is part 1 of 5. This is the introduction to the material. So we begin by asking, what is attribution and why might we do it? So if there's been a weather or climate extreme event that's occurred, there's a lot of media and public interest in asking how much anthropogenic climate change has contributed to the change in the probability or the magnitude of the observed event, and how often similar events will happen in future. So that's the core idea behind what we're trying to do here. And a specific weather and climate extreme event cannot be solely attributed to a single cause, and you'll see in the next few slides that is because weather variability plays a big role. But it's still possible to estimate how certain factors like the effect of anthropogenic forcings may have modified the probability and contributed to the magnitude of the event. And that's the key things we want you to get out of this workshop. Attribution is a process of evaluating the relative contributions of multiple causal factors. So there might be several drivers that are causing risk change to a change or an event with some statistical confidence. So that it's a statistical process. Because it's very model heavy, particularly through event attribution, we also have to ask questions about the reliability of models when we do so. In this workshop, we largely focus on just two causal factors, human forcing and natural forcings, or relative to natural forcings. In other things you might consider are, well, we could break human forcings up into various things, so aerosols, greenhouse gases, land and surface changes, ozone, or we could imagine natural forcings. We can break that up into several different things. So we might think about volcanoes versus solar versus anything else that you might think is natural. So here's a lovely schematic from Otto et al., which provides sort of steps to attribution. So the first step is to ask what happened. This is in a couple of events. So that would be about analysing observed data, reanalysis, looking at reports on impacts. And that's a really important first step. If you don't do this, then you don't have any idea what happened and you can't really engage with the event, as it were. Step 2 would be about event attribution. To think about which region, so this is a precipitation anomaly in South America, and here in coastal Brazil. So we might think about which region, where did it happen, what variables are we thinking about, and how rare was the event. We might then ask, well, what about model evaluation now, because we're going to start using models to do these calculations. So there's the model itself. Here's some different observations for this part of the world. Here's the model spread. So we can ask, well, does the model include key processes? Does it reproduce the statistics? We might have an expectation that the model that we're going to use in this study does a pretty good job in many of these things. It's high resolution, but it does have its flaws. So I think it's well worth thinking about model evaluation, and I'll say a little bit more about that in the example I present. Step 4 might be to estimate the likelihoods. This shows return times. So we might do this by calculating the change in likelihood for different return times, and we want to use as many methods as possible in general. Again, for this workshop, we effectively get you to use one method, but if you then go on and do these studies independently, you'll be able to explore more methods. So step 5 is to interpret and synthesize. So what is the overarching result? How robust are the results? And then step 6 is to communicate this. How to communicate confidence, who's asking the questions, and so those are the sort of steps. This is a schematic. This is from Hospital, which goes all the way from identifying what actually happened through to communication to a broader audience. We don't really stress this part very much in the workshop with effectively a week of your time, or half time over 2 weeks. We can't really get you to go all the way through, but I think that's something you might want to reflect on near the end of the workshop. So the the approach we take is we imagine some climate variable here. We define some threshold. So we say that the event is extreme that we're interested in if it's greater than this threshold. That's essentially the definition. So here maybe this is the relative likelihood. So these are probability density functions. So here's the actual world, say, with a peak there and then a decline on the other side. And here's the counterfactual world, so maybe the natural world, the world that didn't occur. And one issue you might like to think about is this is not actually observable while this is. So we then say, here's our threshold. So in the counterfactual world, we work out the probability of being above that threshold, P0. We have the actual world, we work out the probability of being above the threshold, and essentially current literature stresses the risk ratio P1 over P0, the probability of the event in the real world, relative to over the probability of the event in the natural world. Because we're looking at actual events that occurred, we can think about the thresholds that are relevant, and we know those cause damage, and so the thresholds here aren't arbitrary, they're based on damaging events. So the risk ratio is essentially how much of human activities increased the occurrence rate of the event. So it might be 20% sometimes, it might be minus 30%, maybe they made it less likely, it might be 10 times. So we've seen all of those in previous workshops. The early literature uses concepts of fractional attributable risk. FAR, that's 1 minus P0 over P1. This quantifies the fraction of events attributable to human-caused climate change. So that matters when you think about loss and damage issues. So now I'm going to kind of talk through a Russian heatwave event, and I'm choosing to do this because this exemplifies the importance of framing the question, and also how different different approaches can lead to quite dramatic conclusions that are seen on the surface very differently here. So this is about framing the question. So here is Eurasia. This is I think satellite data. So this is surface air temperature anomalies from July 20th to 27th, 2010, compared to the normal conditions 2000 to 2008. So you can see this really high hot region here in Eastern Europe, basically in central Russia. I think Moscow is about here, St. Petersburg is there. So this is sort of an into the Ukraine. So question is, we might first ask, well, why did this happen? Well, the principal drivers of this would be reduced cloud cover, which in turn led to increased solar radiation. How do you get reduced cloud cover? Well, you need a persistent block, so a long-lasting block. Increased solar radiation that you get from the reduced cloud cover leads to drier soil and higher temperatures, because more of the energy gets turned into sensible rather than evaporating water. Okay, so then say, well, did human-induced climate change cause this? So this is an ill-posed question. We cannot, for a single event, say humans caused it, because those kind of events, those circulation conditions, happen regardless of human influences. So I think that's a key idea. We're not talking about cause. Instead, what we're doing is we're asking, did human-induced climate change modify the probability of this event? So it's attribution of risk, not cause. So a lot of the earlier detection attribution work I did, it was, in the end, we had very high confidence on what had happened for a broad set of climate changes, and so we could talk about attribution of change. But here we're talking about attribution of risk, so the shift in probabilities. And then another question we can ask is, did human-induced climate change contribute to the severity of this event? Did it, an attribution of magnitude, so how much did it move, say, the average temperature of extreme events? Might be another question one can ask. We will mostly in this workshop focus on attribution of risk. So continue with the thought about framing the question. Let's begin with all weather events are unique. If you look in detail at any weather event that has occurred, there will be nothing identical to it in the record. So they're all unique. We have to classify. And all extreme and damaging events have a strong circulation component to them. But I think if you look around the literature, you will see that extreme events are associated with strong circulation of one form or another. So to first order, all events are largely caused by circulation. So we need to think about the probabilities. And so therefore, how do we think about the role of human-induced climate change in events? What is the actual event itself becomes a key question. And in previous workshops, we found that participants have taken quite a while to work out a sensible definition of the event. That's been quite iterative between them and their tutors, between them and their organisers and the other groups who all chime in. So don't be afraid that's going to take you a little while to get to grips with.